Hi, everybody. Today we are doing a short lecture for that corresponds with chapter 3 or chapter 5, part 3 of our PowerPoints, and corresponds to section 5.7 in our textbook, the title of which is A More Realistic Model for the Operational Amplifier. And what we're doing here is we're just finishing up chapter 5. We are also finishing up the material before the midterm exam. So what we have here is the last lecture that we're going to have before midterm. And so we're sort of closing the chapter, so to speak, on the first half of our material in electric circuit analysis. So having said that, this is an extremely short lecture today. There's only 4 PowerPoints in this section, but basically what we're talking about today is just using, when they say a more realistic op-amp model, it may have occurred to you as we're going through this material that the model for the op-amp that we're using, we have to assume linearity, we have to assume we have to assume that there's this negative feedback loop where we can't really proceed unless we have negative feedback, and we're assuming specifically that the voltages and currents are 0 or infinite, which is not necessarily realistic. So what we're doing in this last section is going back to our old methods of analysis and just doing the analysis using the older methods, KCL and KVL, and Ohm's law, and then comparing the results from the realistic analysis to the results from the ideal analysis. So having said that, the first is we take a look at this op-amp, and the question is, which configuration is shown here? All right, so the first thing is we have an op-amp, we have the inverting terminal, the non-inverting terminal, we have an output, and we have 2 power inputs. And if you notice, the negative feedback is associated with the power source. So that is the criteria for which, first of all, we can consider this to be ideal, at least at first blush, and second, that it is an inverting amplifier. That means that the voltage from the output is going to have the opposite sign of the current of the voltage from the input. So the first thing it says, let's suppose that V sub G, which is the voltage at the source, is 0.5 volts. Assuming the op-amp is ideal, what is V sub O? What is the output? Well, let's just run through that calculation really quickly so that we just sort of have a good basis for what we're doing. And this page is also on your Moodle page. But as you can see, I've redrawn the circuit. I've redrawn that op-amp. V sub G, the voltage at the source, is 0.5 volts, and we want to know what is V sub O. So I've gone through the procedure. The first is we have to check for negative feedback, because if we don't have this negative feedback loop, we can't analyze the circuit at all. So check. Next thing is we need to write Kirchhoff's current law for the inverting terminal. Okay, so we have the current that's passing through the 5 kilo ohm resistor and the current that is passing through the 100 kilo ohm resistor and the current that is coming or going out into the negative, the inverting terminal, and the 3 of them have to equal 0. So in other words, we're doing an analysis right at this node right here. Well, we can calculate the current over the, I don't know why I said 25, this should be 5 ohm resistor, and I've used 5,000 here, so that's correct. So we have 0.5 volts, voltage over resistance equals current, and we get 1 times 10 to the minus 4 amps. And then with the 100 ohm resistor, the current there would be whatever V sub O is, right? Because that's the only, at this node, that's all we have. V sub O over 100,000 ohms is equal to that particular current. And we also know, because we're doing an ideal analysis, that I sub n is equal to 0. So if we go back to KCL, we can see that the the current through the 5 kilo ohm resistor plus the current through the 100 or across the 100 kilo ohm resistor has to equal 0. And so when we bring this over to the other side, it becomes a negative, or I5 equals negative I100, which would be expected because it is it's an inverting it's an inverting amplifier, op amp. And when I do my solution, I get that V sub O is equal to negative 10 volts. So there's some really good things about this number. First of all, it is between the two voltages of the VCCs. It's between 20 and negative 20. So for that reason, we can assume that, or it is in the linear region. And the other thing is well, I guess maybe I'm just going to say that. We're just going to say it's in that, so we can say that our analysis using an ideal method is correct as far as the ideal analysis goes. All right, so then the next step here is to compare, if we think about that, here we go. If we find that, and you see, here's our op amp, and we find that the current, the voltage is negative 10, just like we said from our work before. We want to compare that to the voltage we would calculate using old standard methods. So here, instead of looking at it as being an ideal amp or an ideal circuit of any sort, we just go through the process and do the analysis here at node A, and we do the analysis here at node B. And when we combine those, we can see that we can solve for V sub n. And when we do that, or excuse me, V sub O, pardon me. And when we do that, we find that V sub O is negative 9.999 and some change volts. So if we compare that to our calculated value, which I'll just sneak back here to negative 10, those are essentially indistinguishable from each other. They're very, very close, and the conclusion to draw is that using the ideal methods of calculating op amp in the linear range are actually quite good, produce quite good results. All right, that's it for chapter 5. That's it for the first half of our material. And I am looking forward to continuing on after midterms. We'll have spring break, and then we will start talking about inductors or capacitors, both, but I don't remember which comes first, but it's always fun. All right, you guys have a wonderful day, and look forward to seeing you in lab.